Okay, hello everyone. We're looking at our second video on pulleys, and we're linking this into a topic which I like to call two-step SUVAT. The reason why I refer to it as a two-step SUVAT question is because there's going to be an event in this question that causes the acceleration to change. Now, SUVAT is linked to constant acceleration. So if the acceleration changes from one scenario to the next, there's been one SUVAT for the first scenario and a second SUVAT in the second scenario. So what we're looking for here is a situation in which the forces are going to change from the original scenario, causing a change in acceleration. Now what I have for you in front of us is a pulley system with a 9 kilogram block on the left hand side, that's particle P, and particle Q on the right hand side, which is the 4 kilogram block. And both of the particles are 2 meters above the ground. Now our starting question is still to find the tension and acceleration of the system, and then to find the speed of the particle when it hits the ground. It hits the ground. So for this to happen, we need to treat this as if we were doing our previous pulley questions and label our forces. So 9 kilogram block has 9G down on the left and tension coming up. And the particle on the right hand side has 4G acting downwards and tension acting up over here. And because we know that the particle on the left, 9 kg, is going to accelerate downwards, we have our double arrow coming down, and on the right, our double arrow coming up. So, as previously, we can do F equals ma on these particles. If we do F equals ma on P, P is coming down, so our positive force is our 9G. Our negative force is our tension, 9G minus T, is equal to 9A. Then we apply the same principle for F equals ma on Q, but Q is going up. In this case, it's T minus 4G is equal to 4A. Exactly what we did previously. To solve these two questions, we need to add the two questions or add the two equations. So if I write them again on the right hand side, that gives us 9G minus T is equal to 9A. T minus 4G is equal to 4A. We add our two equations, we get 9G adding with minus 4G is 5G. 9A plus 4A is 13A. And that value of A is equal to 5G divided by 13, or 5 times 9.8 divided by 13, which is 3.769 meters per second squared. 3.769 meters per second squared. Now that's given us our value of A. We now need to work out our value of tension. So we simply substitute back in over here. So I'm just over here. Substitute our value of T back in. So T is equal to, or T minus 4G is equal to 4A. So T is equal to 4 times by 3.769 plus 4G. And if we do that on our calculator, we end up with a value equal to 54.28 newtons. 54.28 or 54.3 newtons. So that's our acceleration and our tension that we've worked out in part A. Now part B refers to the speed of B as it hits the ground. So if we're bringing speed into this, we're talking about a distance from where it's going to hit the ground. we must be linking this to SUVAT. Now, the reason why we call this a two-step SUVAT is going to come into what happens in part C. So we are just going to work out what's happened in part B first. Now for this, I no longer need to worry about these equations over here. The only thing I need to worry about is the acceleration of the system. And if we apply the values of SUVAT that we've worked out, SUVAT, we know the distance traveled in this case is 2 meters. The initial velocity is 0 because it starts from rest, and the acceleration is 3.769. From our last video, or even just by looking at the formula here, we can see the final velocity here is going to be equal to, or using the formula, v squared equals u squared plus 2as, and that is going to give us v squared is equal to 0 squared plus 2 times by 3.769 times by 2 again. Let's worry about that. So we work that out. We get times by 2 times by 2, and then square root our answer. We get a value of 3.88 meters per second. So v here is equal to 3.88 meters per second. Now that's a very, very important value we've worked out there, and you'll notice I've actually added it into our SUVAT over here. The next part comes down to understanding what happens when the 9 kilogram block hits the ground. I've already said this is a two-step SUVAT. Now, when this particle hits the ground, the 9 kilogram block is going to go downwards. The 4 kilogram block is going to move upwards. They're both going to move 2 meters. This is going to come down 2, this is going to come up 2. But when a particle hits the ground, the only reason this is moving is because the 9 kilogram block is moving downwards. What happens to this is that when this moves up and this hits the ground, the string goes slack. There's no pull anymore. If there's no slack and no pull, the tension disappears, which means that the only force acting on this particle now is the 4 kilogram. And that is similar to a particle or a situation of free fall. And I'll show you how we derive that in a moment. But what we have, or a very, very key important thing to note, is that you'll get questions where particles will hit the ground, and you'll get questions where strings will get snapped. And what we need to understand is that when a particle hits the ground, the string goes slack and tension disappears. So these T values become 0. It's the same as if the string was cut, there'd be no tension anymore. Now, what most people think is, okay, this tension disappears, the particle Q is going to have no more speed associated to it. We've got to remember that the speed of both P and Q has increased over the period that it's been moving. For those 2 meters, this stopped at a velocity of 3.88 down here, and this would have moved up to a speed of 3.88 over here. Which means that now, when we look at our particle, we have our particle Q, which is 4 kilograms, and the only particle, or the only force acting on it, is the weight, which is 4g. That means that this particle is actually moving upwards, but it only has this weight component acting upon it. So if we did F equals ma on this now, we'll do that here, F equals ma upwards, because it's still moving upwards, our force would be minus 4g, because acting in the opposite direction, is equal to 4a, meaning our acceleration is now minus 9.8, just like a normal free fall question. And that's very, very key, because now the acceleration has changed. And we said this has become a two-step SUVAT. So I'm going to have a second SUVAT, which I'm going to write on the right hand side, SUVAT. Now what we know, or we're being asked for, is the greatest height reached by Q. Now when something reaches its greatest height, it's had some sort of speed which has then decreased to 0. So the final speed of this particle is 0. The acceleration is minus 9.8. What we need though, or what we're looking for, is the value of S. Now I don't have enough values there to work out my SUVAT, but in the case of a two-step SUVAT, when this particle P hits the ground, Q has increased its speed to 3.88. So the final velocity of period 1 becomes the initial velocity of period 2. This is always the case. The final velocity of the first section becomes the initial velocity of the second. And we can see from this very clearly that if we are trying to work out the distance or the greatest height reached by Q, we're again using V, U, A, and S. So this is going to be V squared equals to U squared plus 2AS. V squared in this case is 0, U squared is the 3.88 squared, plus 2 times by minus G times S. If we take this to this side, we get 2GS is equal to 3.88 squared. So S is equal to our velocity squared and then divided by 2g, which is equal to 0.769 meters. 0.769 meters. Now that's almost done. We're almost done. Last thing we need to work out. It said the greatest height, but it means the greatest height above the ground. Now we knew these particles were 2 meters above the ground. Initially, P went down by 2 meters and Q went up by 2 meters. That means Q is now 4 meters above the ground at this point over here. Then it moves this additional 0.769. So our final answer for this case is 4 plus the 0.769 meters, which is 4.769 meters. That is your final answer. So, quick final review of this just to reiterate what we've done. We worked out the tension and acceleration via simultaneous equations. We then created our two SUVATs, and we said the final velocity of the first SUVAT became the initial velocity of the second. But it's very, very key for us to understand that when the particle hit the ground, the string went slack and the tension disappeared, and we had to work out the new acceleration. In other scenarios where we're not dealing with pulleys like this, but pulleys on either rough surfaces or inclined planes, or even on horizontal rough surfaces, the acceleration will not be equal to minus 9.8, it will be equal to other values. I hope that's made sense. If it hasn't, please comment below or let me know.